Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to provide an example of how to use these two equations here to calculate the velocity of a point in space and the tangential acceleration of a point in space due to the rotation and angular acceleration of this object that point is on. So what we're looking at here, we've got this object which is 0.4 or actually 0.8 meters by 0.6 meters, and imagine that it's welded to this bar, and this bar is rotating about this axis at 14 radian per second and accelerating at 7 radian per second squared in the same direction. And what we're going to try to do is calculate the velocity and acceleration of this point that I called P out here using these formulas here. So first thing I'm going to do here is work on finding the angular velocity vector and the angular acceleration vector in kind of Cartesian format here. And there's an angle theta between this bar and this geometry, and if I'm looking at this triangle right here, this distance along this triangle is 0.3, the height is 0.6, and I've already calculated the hypotenuse. That makes the hypotenuse of that triangle 0.67. So what I'm going to do is use this triangle here for my sines and cosines as needed. Now, the angular velocity vector by right-hand rule points along this shaft up and to the right. So in my picture here, the angular velocity vector actually points this way, and so does the angular acceleration. So the angular velocity vector in Cartesian format can be written, let's see, the hypotenuse is 14 radian per second. I'll write the units last. Times cosine theta, which is going to be give me 0.3 over 0.67 I, and then times sine theta, which is going to give me 0.6 over 0.67 J. Now I haven't thought about pluses and minuses yet, I just did components. The x component actually points back this way, where I've got plus x this way, so I'm going to go ahead and put a minus sign there for the fact that that x component is negative. Whoops, and I called it the y component. I'm sorry, I've got the y-axis pointing this way. That actually would be the z component. So I'm going to tack the unit vector k onto this. So what I'm going to do here is I'm going to take a moment, pause this, calculate values, and I'll be right back. Okay, so that didn't take long. So again, all I did is went ahead and distributed this. So what I have here is I have my angular velocity vector now, minus 6.29 I plus 12.54 K, and I'm just going to do the same thing for the angular acceleration vector. Now the angular acceleration vector again is along this axis, points in the same direction as the angular velocity. So the angular acceleration vector can be calculated by taking 7 times this same exact expression here, minus 0.3 over 0.67 I plus 0.6 over 0.67 K. And I guess I'll go ahead and take the time to just get values here. Okay, so I got negative 3.13 I plus I get 6.29 K. And the units on that would be radian per second squared. Okay, so I've got the angular velocity and the angular acceleration vectors for this object. And this is one rigid object here. This is a weld here. So that's these angular velocities and angular accelerations are for really the entire object. Next, I'm going to calculate the position vector, which points to P. So in this picture, that would be this vector right there. And I'll go ahead and leave that. So that position vector, let's see, x direction, we're going this far, so that's 0.3. So that's going to be 0.3 I. Y direction is this distance, and we're in the minus y direction, so I'm going to put minus 0.4 J. And that would be in meters. So now to calculate the velocity of the point P, we're just going to take the angular velocity cross with the position vector. So that is going to be this vector crossed with this vector. So I'm going to write that out, minus 6.29i, and what I'll do is I'm going to put the units last, plus 12.54k crossed with our position vector, 0.3i minus 0.4j. And I'm just going to do this. Unit-wise, we got radian per second times meters. That's going to give us radian meter per second, and a radian is a dimensionless quantity. So that's going to work out to meter per second. All right, and now we're just going to have to go through and do the cross product here. So the first term, and again, when I do cross products, I just do them like FOIL method. You know, a lot of people like to use determinants, and there's nothing wrong with that. And I think it's good practice just to go ahead and do the cross products kind of as is. So that first term, we're going to have this crossed with this, which is 0 because of the I cross I. Next, we're going to have this guy crossed with this guy. So that's going to be minus 6.29 times minus 0.4, and now our direction is given by I cross j, which is k. If you don't know where I'm getting that from, go back and look at my video on crossing unit vectors. All right. Now I'm going to deal with, oops, I'll do this in blue, this guy. So when we do this guy times this guy, we're going to have 12.54 times 0.3, and then the direction is k cross I, which is j. Next term, we got this guy and this guy, so that's going to be plus, oops, I don't need another plus. That's going to be 12.54 times minus 0.4, and our direction is coming from k cross j, which is minus I. And again, our units on that, meter per second. So what I'm going to do is I'm going to take a moment, try to keep this video short. I'm going to pause it and calculate values. All right, I'm back. So here's the values I got. Hopefully they're right. I got 2.52k plus 3.76j plus 5.02i meter per second for the velocity vector of this point. Now you'll notice that all these terms come out positive. So again, if you imagine, this point and look at the rotation and think about the direction this thing's going to be moving, that velocity vector is kind of pointing maybe something like, maybe something like this, and it's definitely going to have an angle kind of in the positive z direction with respect to that plane. So just kind of looking at the picture, I would expect all those velocities to come out positive. That doesn't prove it's right, but it does look reasonable compared to my picture. All right, now next we're going to work on the acceleration vector. Before we do, however, I'm going to try to get myself a little more room here. All right, so now for the acceleration vector, I'm going to calculate that basically the same way, except we're going to take the angular acceleration and cross it with our position vector. So the angular acceleration vector was here, minus 3.13i plus 6.29j, k, be very careful about that. And again, that would have units of radian per second squared. I'm going to tack the units at the end. And we're going to cross that with a position vector, which was 0.3i minus 0.4j. And that was in units of meters. So by the time we take radian per second squared times meter, we get meter radian per second squared. Radian is dimensionless. So unit-wise, that's going to work out to meter over second squared. All right, I'm going to go ahead now and do the cross product. So the first term, when we take this crossed with this, we get 0 because of the I cross I. Next term, we're going to have a minus 3.13 from this times minus 0.4 from this guy. and the direction is coming from I cross I, oops, I'm sorry, I cross j, which is k. All right, now we're going to do this guy times this guy. That's going to be plus 6.29 times 0.3. The direction is coming from k cross I, which is j. And then we got this guy times this guy, so that's going to be plus 6.29 times minus 0.4. Direction is coming from k cross j, which is minus I. I'm going to end unit-wise, again, meter over second squared. I'm going to take a moment now and pause this and calculate values. Okay, I'm back. I went ahead and calculated values, and again, for this product I got 1.25 K. For this product I get 1.89 J, and for this product I got 2.52 I. Again, units on each term, meter over second squared. So again, let me kind of recap what we did here. So I was trying to demonstrate how to use these vector formulations of these equations to calculate the velocity and acceleration of a point in space due to the rotation and tangential acceleration of this body. Keep in mind that this acceleration is not the net acceleration of this object, because there's also centripetal terms and conceivably Coriolis terms in another problem where you know, that's not taken into account. This just gives the tangential acceleration. And to do that, we started by finding a position vector. That position vector really can be to any point along the axis of rotation here, but this was a nice, logical, easy point to choose. Then we wrote out the angular velocity vector in Cartesian format, and then the angular acceleration vector also in Cartesian format, which gave us this. And then we just did the cross products, omega cross r, alpha cross r. So I hope this video helps demonstrate how to calculate the velocity and acceleration of a point on an object due to its rotation and angular acceleration. Have a great day.